All right, let's get right into it. We are talking about the Riemann hypothesis. It's one of the biggest, baddest unsolved problems in all of math. You solve it, you get $1 million. But honestly, it's about so much more than the money. You'd be solving a deep, fundamental mystery about how prime numbers work, a puzzle that has stumped the greatest minds for over a century and a half.
But what if there was a secret way in, a kind of back door to this whole thing? What if you could take this incredibly complex, abstract puzzle and turn it into a question that's really just about, well, finding the divisors of a number and adding them up? Yeah, I know, it sounds way too simple to be true, but believe me, it's the key to this entire mystery.
And that's what brings us to the divisor's secret. You see, back in the 1980s, there was this huge breakthrough. It completely transformed the Riemann hypothesis from a problem about some really abstract stuff into a concrete, testable rule about regular old whole numbers. Turns out the biggest clue was hiding in plain sight the whole time.
Now, the main tool we're going to use for this investigation is something called the divisor function. You'll see it written as sigma of n. And it is super straightforward. All you do is take a number, n, find all the numbers that divide into it evenly, and then you just add them all up. Seriously, that's it. That's the function.
Let's just do a quick example so you can see it in action. Take the number 12. Okay, so what are its divisors? You've got 1, 2, 3, 4, 6, and of course 12 itself. Add all those guys up, and you get 28. So sigma of 12 equals 28. And this simple little act of adding up divisors, that's what holds the key to the whole $1 million mystery.
So here's the secret clue itself. A French mathematician named Guy Robin took that simple sigma function and stuck it inside this thing called an inequality. On one side, you have our sigma of n divided by n, and on the other, you have this term with logarithms, which are just a handy way to deal with really big numbers, and this other special number. Now, it might look a little intimidating, but what it means, oh man, that's the profound part.
And this is where it all clicks. Robin proved that his inequality and the Riemann hypothesis are basically two sides of the very same coin. The Riemann hypothesis is true if and only if this inequality holds up for every single integer bigger than 5040. Just like that, this massive abstract problem turns into a manhunt, or a number hunt. We just need to find a single number that breaks this rule.
So, if we're gonna hunt for a rule breaker, a counterexample, we've got to know what we're looking for, right? We need a profile. We can't just go around checking every number one by one. That's impossible. We have to be smart about this. We need to figure out who the prime suspects are.
So mathematicians started building that profile, focusing on numbers that have just ridiculously large sums of divisors. First, they looked at abundant numbers. Then they narrowed it down to an even more exclusive club, superabundant numbers, which are constantly setting new records for that divisor sum to size ratio. And finally, they isolated the most extreme of the extreme, the colossally abundant numbers. These are our guys. These are the prime suspects.
And this right here, this is probably the most important lead in the entire investigation. Robin proved that if a counterexample is out there, if there's some number that can break his inequality and prove the Riemann hypothesis is false, it absolutely, positively has to be one of these colossally abundant numbers. The search just went from an infinite ocean of numbers down to a very specific, though still infinite, list of suspects.
Okay, so with a clear list of suspects, the investigation could really kick into high gear. Researchers basically created a digital dragnet. They unleashed massive computing power to systematically track down these colossally abundant numbers, and some of them are just astronomically huge, and then check every single one to see if it breaks Robin's rule. And this graph, this is the forensic evidence from that dragnet. Think of that zero line as the point of no return. If any of our suspects, those little circles, dip below that line, boom, the rule is broken and the Riemann hypothesis is false. And as you can see, they get so close, tantalizingly close. But so far, every single one has stayed on the right side of the law.
Now, we're looking at the same thing, but it's like we've put it under a microscope. We're talking about unimaginably large numbers here. And yeah, you see them bouncing around like crazy, but look at the overall trend. It stays firmly on the innocent side of that line. Every single suspect that we have ever put to the test has a rock-solid alibi. Well, so far.
For a long time, the case just seemed to be about checking more and more of these suspects. But then, something incredible happened. A stunning new discovery that completely changed how we look at this entire investigation. It wasn't just about the suspects anymore. It was about all the other numbers.
So in 2007, a mathematician named Marek Wojtowicz published this totally game-changing proof. He showed that the set of numbers that are innocent, the ones that aren't even close to being counterexamples, has something called an asymptotic density of 1. What does that mean? It means that if you just picked a number at random, the chance of it even being a potential suspect is basically 0. The implications of this are just staggering.
So, to really get your head around what this means for our number hunt, you have to completely change your sense of scale. It tells us that these rule breakers, these counterexamples, they aren't just rare. They are so rare, they're almost statistically non-existent. The proportion of numbers that could possibly break the rule just shrinks away towards nothing.
Look, this discovery completely changed the game. We used to think of this as looking for a needle in a haystack, right? Well, Wojtiewicz's proof showed us that no, we're actually looking for a single atom in an almost completely empty galaxy. Counterexamples aren't just rare, they're infinitely rarer than anyone had ever dreamed. Almost every single number is innocent.
So, after all of that, where does that leave us? Where does the case stand right now? Well, the $1 million prize is still out there, and the mystery is still officially unsolved. But this whole investigation has given us this profound new appreciation for the landscape of numbers.
Let's just quickly recap the key evidence. We've seen how this super complex hypothesis can be boiled down to a simple test involving a numbers divisors. We've identified our prime suspects, the colossally abundant numbers, and found that everyone we've checked so far is innocent. And maybe most amazing of all, we've learned that nearly 100% of all numbers aren't even candidates to break the rule. The place where a counterexample could even hide has shrunk to an almost unimaginably small corner of the universe.
All of this work, this entire incredible investigation, has uncovered this deep, hidden order in the world of numbers. All the evidence seems to be screaming in one direction. But it does leave us with one last fascinating question. Does all this make it more likely that the Riemann hypothesis is actually true? Or could it be that it's just really, really good at keeping its secrets?